Welcome back to our series on applied regression analysis. I'm Mark Ledbetter. This is lecture video 28. We're in chapter 8 and multiple regression. We're finishing up the introduction to that. And last time we talked about how to determine the best equation. We looked at the least squares criteria for the multiple regression and the multiple correlation coefficient. This time we're going to look at the ANOVA table and start looking at some examples. And so the ANOVA table looks right here exactly like it does for the straight line regression. The difference is that we have a source of variation down here the same way. We have model, error, and total. So the difference is how y hat is calculated. So now we have multiple explanatory variables included in there. But the regression, the ANOVA table, is basically the same. We have the SSR, which is the sum of squares for the model or regression. And then we have SSE, the errors, and SSY, the total. And we calculate the mean square model or regression as SSR divided by the degrees of freedom. There are k degrees of freedom because there are k variables. Before there was one variable and 1 degree of freedom. Now there's k. And you know that the degrees of freedom have to add up, and the total degrees of freedom are n minus 1. And so n minus 1 minus k leaves us the error, which is n minus k minus 1, the leftover, so to speak. SSE, the MSE, the mean square error, which is an estimate of our variance, is SSE minus its divided by its degrees of freedom. You take the ratio of MSR and MSE, and that creates us an F statistic. And this is the F value for the table. And we compare that to the critical value. And the P value is the probability that F is greater than our F value. Okay? So so we have, if we reject H naught, if our F value is greater than our F critical value. So this is the rejection region here that we need to know. And we have the same partition as before. SSY is equal to SSR plus SSE. Okay. And we still calculate R squared the same way. SSY minus SSE. Now I want to point out that SSY minus SSE is SSR. So this is really equal to SSR over SSY. So there's a shortcut. If you have an ANOVA table, you just take SSR divided by SSY. However, you have to be careful with that, because if we add more things to the ANOVA table, then you have to come back to this. So this is a shortcut for this model, multiple regression model. But again, if we start doing ANOVA, then we wouldn't be able to do that. All right, and obviously R squared is between 0 and positive 1. Now let's look at a numerical example here where we have the weight, and we're trying to estimate weight based on height. And so this would be our y, and this is beta naught plus beta, and this is our x1 variable here, okay, height. And so we have an ANOVA table. Notice that our R squared is here, 0.663. Our SSY is here. This is corrected total is what that's called. And then our SSE is here, so you'll notice that. And we have our degrees of freedom. And then SSY minus SSE is right here. That's our SSR, SS regression, or sum of squares for the model. Okay. And then we have the mean square here, which is, you can see that 588 divided by its degree of freedom 1 is still it. And then if you take 299 point all of that divided by 10, you see that that's what you get, 29.9, etc. And again, you take 588.9, etc. Divide by the 29.9, etc. And you get the F value. And then here is the p-value. And we like small p-values because this is the probability that we would get this F value under the null hypothesis. And the null hypothesis here is that beta 1 is equal to 0, okay? Because we only have one beta in the model, okay? Here is our estimate of beta not hat. These are our parameters, and these are the estimates, okay? So we have our intercept, so that beta not hat. We have our height, which is our x, x1, and so this is the beta 1 hat. And we have, this is S sub beta not hat, and this is S sub beta 1 hat. And then we have our t value, and we have the p value here, and the intercept's not significant, but notice that this p value and this one's the same because they're the same because there's only one variable in the model. Now, if we look at age, we see that we have a lower r squared here, and we have a 0.0034 whether we had a 0.0013. So the p-value is higher, so we're less significant with age, but age is significant. Now let's look at age squared, and it also is significant, okay? And again, we have an r squared that's even a little lower. So what would happen if we take and look at a model with age, height, and age? Then our r squared increases to 0.78, a little under 78, okay? Now, I will tell you that every time you add a variable into the model, r squared is going to increase no matter what. So r squared is a measure of the fit of the data, right? How much data is explained by the model. The more variables you put in, the more you explain. Even if they're not very good fitting variables, they will explain something. So we have to be careful. Now, our p-value dropped to 0.0011. So that's actually lower than the first one. So this is more significant. Having the two variables in there is better than just having the one, the height. So, and then when we add age squared to height, it's still highly significant. But so whether we have age or age squared in the model, we have two variables with very close to the same. This one's slightly better, 0.7799, 0.7764. And then finally, we add all of them in there, age, height, age squared, and the p-value jumps back up. And the r squared, though, it goes up a little bit because, again, we added more variables. So we want to do this example here. And I've got the data, and so we have the different models. Here we have, this is the systolic blood pressure on age. This is the systolic blood pressure on age and smoking. So these are our explanatory variables. This is our response, explanatory variable. And so we don't have r squared given here. We're going to have to calculate that. And here we have age, smoking, and QIT and on our response systolic blood pressure. So let's see what the questions are. This will help us answer some homework questions. So it says the multiple regression relationships of here and here are studied using the data in problem 2 of chapter 5. So you did some of this for homework. The three regression models are considered yielding least squares estimates and ANOVA tables that we just saw, right? So use the model that includes all three independent variables, x1, x2, and x3, and we've just given x1, x2, x3, to answer the following questions. 1, what is the predicted systolic blood pressure for a 50-year-old smoker? So this is smoke equals 1. This is age equals 50 with a QIT index of 3.5. So QIT equals 3.5. So let's do that. So for the first model, we want to find our regression equation. So we have y hat equals. We need to go up here and for all three of them, right? And so here we are with all three. Here's our intercept, 45. This is going to be beta 1 hat, this is beta 2 hat, and this is beta 3 hat. That's these variables here, values here. So we write those down, and then x1, so x1, x2, x3. So there we have it, 45, the 1.213, we rounded to 3 decimal places. And this is for age, x1. This is for smoking, oops. And this is for QIT. And so what we do is we decided that we wanted a smoker, that's 1, so we put in a 1 here. And age is 50, so we put in 50 here, and a QIT of 3.5, and that goes here, and so we have a response of 145. Now, what's the predicted value for, again, a 50-year-old, but now non-smoker, so smoke equals 0, and QIT still 3.5. So we plug those in, and we go down, we predict that the systolic blood pressure will be 10 points lower. So just by not smoking, that would give you an, on average, 10-point lower blood pressure, which is significant. And so now the third question is, for a 50-year-old smoker, estimate the change in systolic blood pressure corresponding to an increase in the QLIC index from 3 to 3.5. We already have the 3.5, so we already have this value. So what we need is the 3.0, smoker 50. We get this, and so the difference is going to be from 3 to 3.5. The SBP increases, right? It goes up from 141.4 to 145.7. So that's by an estimated 4.296 points from here to here, okay? So that's how we answer that. Now, using the computer output, determine and compare the R-squared values for the 3 models. If you use R-squared and the model simplicity, this is also called parsimony. That's the more commonly used term, parsimony. It means, parsimonious means like smaller or less complex or less. So we want less number of variables. As our criteria, which of the 3 models appears to be best? So R squared is this. It's also equal, in this case, to SSR divided by SSY. So that's the easiest thing to do. They have calculated it out using the SSY and the SSE. This is age on SBP. So we will scroll up here to age on SBP, and we could just take this value divided by this value, and that looks like a little over half. And let's see what we got. And so, yep, 0.601. And then we do the same thing for age and smoking. So I'm sorry to scroll so much, but I do want to show you. So age and smoking's here. And again, we could take these two, subtract these two, and that gives us this, divided by what's on the bottom. Notice that the SSY stays the same in all the models, because that's the total variation. It never changes. So this value is always the same. What changes is how much is in SSE versus SSR. Okay? And so here we have 4689 divided by 6425. And here we have 4889 divided by the same, 64. So this is a little higher, so it's going to give us a little higher R squared, and we expect that because we have more variables in there. The question is it enough to want to include the extra complexity of that extra variable in there? So here we have age and smoking 0.730 for our R squared, and here we have 0.761. So there's a pretty big jump here. So I would definitely want this one. And then the question is, QIT, adding in QIT gets us 0.03 on the R squared. Is that enough to justify making the model more complex to do this? And I don't think it is, and neither did the authors in the book. They said that we would want to use this model. It only has 2, which is significantly better at predicting. I mean, we went from 60.1% explained to 73% explained. But going up to 76.1% explained does not really justify, we think, including QIT. Okay? So That should help us answer our homework problems. Don't forget to scan your lecture notes by midnight, the date listed in the course calendar. Be neat. If you have any questions, you can update your formula sheet if you don't already have some of those formulas on there. If you have questions, come to virtual office hours or email me. If you email me a picture of your work and a picture of the problem so that if I don't have that available, I can help you faster. I hope you'll take care of yourself, and we'll see you next time.